PU2 champions, welcome back to the Brahmastra 2.0 series, and as you all know, in this video we are going to discuss the most important PU2 questions from the chapter solutions, okay? And the best part is I have included all the difficult average questions from the PU2 question bank that is released by the board, so you don't have to worry at all. This one video will solve all your problems. I have given you the questions, how to write the answers, I have explained you, and I have also given you at the end the most important topics that you need to revise from this particular chapter. So yes, this one video is enough. If you are able to solve all these questions from this particular video, then your PU2 solutions chapter is done. Okay, you can trust me on that. So with this note, let's get started with the first chapter, that is solutions, and let's understand its mark distribution. So students, let's first understand the blueprint or the weightage of this chapter and how many questions will be asked, which type of questions will be asked. So first of all, solutions chapter carries 12 marks, and from that 3 will be your BSA, means very short question answer. It can be either in the form of MCQs or fill in the blanks, and rest 3 marker will be your long answer questions. In that 3 marker there will be 2 questions, okay, of theory, means 2 questions will be from the theory, and sorry, one second, just a minute. Yeah, 1 question will be from the theory part, okay, and you will have 2 questions in the numerical part, okay. So numerical there will be 2 questions, and in theory, that is your section C, 3 marker sections, there you will have 1 question from the theory, okay. So we will be preparing for both of them. Now let's see the first 1 marker question. Which of the following statement is false? Okay, the relative lowering of vapor pressure of the solution is equal to the mole fraction of the solute. This is a correct statement. Passage of solute molecules towards the solution side through semi-permeable membrane is osmosis. Now see, passage of solute molecules. Osmosis is about the passage of solvent molecules. So yes, this is the incorrect statement. Next, which one of the following statements given below concerning the properties of the solutions describe a colligative effect? Okay, vapor pressure of the pure water decreases by the addition of nitric acid. Boiling point of pure water, so vapor pressure of the pure water decreases by the addition of nitric acid. Boiling point of pure water decreases by the addition of ethanol. Next, we have boiling point of pure benzene increases by the addition of toluene, and next we have vapor pressure of pure benzene decreases by the addition of naphthalene. Okay, so now see here, in case of boiling point of pure water decreases by the addition of ethanol. So when ethanol is added, what happens? The hydrogen bonding increases, and the hydrogen bonding is disrupted, and that is why we get a what I can say here is deviation happens, okay. But deviations is not a part of colligative property, it is a different concept. So in the point of colligative property, when you have pure benzene and you add naphthalene to that, the vapor pressure of that increases. The vapor pressure of the pure benzene decreases due to the addition of a solute, so that is why option number D here. Next, molar solubility of helium, nitrogen and oxygen are plotted against the partial pressure. Henry's law constant of these gases will lie in the following sequence. So you can see here, if I draw a particular pressure, at particular pressure you can see the solubility. At particular pressure you can see the solubility, and you can see that the solubility of helium, okay, is the least here. So that means the KH value will be, Henry's law constant will be highest for helium, so that is in this option, and in this option this is not there. Next, I think after that it should be N2, and last should be O2, so option number B is the correct answer. Next, pi 1, pi 2, pi 3 and pi 4 are the osmotic pressures of 5% W by V solution of urea, fructose, sucrose and KO respectively at certain temperature. The correct order of their magnitude is, now see here, first of all, what is the formula of osmotic pressure? So I can write osmotic pressure is equal to molarity, that is given mass by molar mass into 1000, right, by volume into R into T. Now see, there is 5% W by V. 5% means this W is 5. Okay. Now whosever molar mass will be higher other all things are constant. Wherever molar mass will be higher, pi value will be lesser. Okay, so but first of all, and all of them except this urea, fructose and sucrose, this KO is a ionic solid. It has an I value. I value here is 2 here. So definitely KO will be the one which is having highest magnitude, so pi 4 will be the one, so I can eliminate these two. Okay, for the other 3 you have to check the molar mass, okay, because this is dissociating, so definitely I value will be there. For all other cases the I value will be 1, so that is why on the basis of I value, first of all I can get KO is the highest one. Now if you see, urea mass is 60, okay, fructose is 180 and sucrose is 342. So which is the least mass? Urea. So urea will have the highest value. So after pi 4 I should have pi 1, then here also I have pi 1, then I should have pi 2, here also I have pi 2, and lastly I should have pi 3. So option number 3 is the correct answer. The mixture which shows positive deviation. Positive deviation means weak interactions, right? So if you have ethanol and acetone, it is the positive deviation because ethanol has strong hydrogen bonding, but when I add acetone to that, in that case the hydrogen bonding is disrupted. Okay, next, concentration terms like mass percentage, ppm, mole fraction and molality do not depend on temperature. However, molarity is a function of temperature because, so if you remember, molarity in its formula has volume, right? And volume depends on temperature. If you increase the temperature, volume will increase and molarity will decrease. So volume depends on temperature and molarity involves volume. Okay, next assertion. Molecular mass of benzoic acid when determined by colligative properties is found high. And molecular mass of benzoic acid when determined by colligative properties is found high. Reason, dimerization of benzoic acid in the solution. Yes. Now see, what happens is, you find that when you add benzene molecules, okay, when they go into the solution, they dimerize, the two molecules become one molecule, okay, and that is why the value calculated will be higher. So both assertion and reason is correct, and reason is the explanation here. The mole fraction of the solvent is this one, the relative lowering of vapor pressure is. Now see, if the mole fraction of solvent is 0.9, then what is the mole fraction of the solute? Mole fraction of the solute will be 0.1, right? And the relative lowering of vapor pressure, that is delta P by P naught, is equal to 0.1, okay, which is your option number A. Next, dissolution of calcium chloride in water is an exothermic process, while that of the ammonium nitrate is an endothermic process. The observation is solubility of calcium chloride decreases with the increase in temperature. Okay, so let us first write down the calcium chloride one. What is its nature? It is exothermic. Delta H is negative here. And for ammonium nitrate, here the delta H value is equal to positive. Okay, so the solubility of calcium chloride decreases. Solubility of calcium chloride decreases with the increase in temperature. Okay, solubility of calcium chloride decreases with the increase in temperature, and that of ammonium nitrate increases with the increase in temperature. Yes, I think that is correct, because here it is endothermic, it will increase with the increase in temperature, and here since it is exothermic, it will decrease with the increase in temperature. Okay, so option number A here. Next we have, when acetone and chloroform are mixed together, which of the following observation is correct? Okay, so AA and BB interactions are stronger. Yes, they show negative deviation. So so here what happens, AB interactions are stronger than AABB. AABB interactions, no, AABB interactions are weaker than AB interactions, and that is why we get negative deviation here. So option number B. Okay, so now let's move to 3-marker question. What is molarity? Okay, so first of all I just discuss. So from here onwards I'll be discussing the 3 markers theoretical questions. Okay, the first question here is, what is molarity, how does it vary with temperature, and write its SI unit. This is very simple question. So how will you explain what is molarity? The first part, molarity, you can write down, molarity is the number of moles of solute, per unit volume of solution. Okay, next, how does it vary with temperature? Number 1 here, how does it vary with temperature? So as the temperature increases, molarity will decrease. Why? Because as temperature increases, volume increases, and if volume increases, molarity will decrease. Now what is its SI unit? It is moles per liter. Okay, fine. Next, state Henry's law, write its mathematical formula and also significance of Henry's constant. So I want all of you to write the exact formula which is given in the book. Okay, exact definition which is given in the book here. So Henry's, at a constant temperature, the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas above the liquid, right? This is the definition. And how do we write it formula? P is equal to KH into X, where P is the partial pressure of the gas, KH is the Henry's law constant, and X is the mole fraction of the gas in the liquid. Now what is the significance of KH? So KH tells you if KH value will be higher. Okay, KH gives the solubility of the gas at a given pressure. So higher KH means lesser solubility. You can see here, I can write that KH is equal to P by X. Okay, so if I have higher KH value, there will be lesser X value. Okay, solubility will be less. So that is the significance. Next, derive the mathematical expression of vapor pressure for a solution of a non-volatile solute in a volatile solvent. Okay, so you have to derive the mathematical expression for vapor pressure of a solution of a non-volatile solute in a volatile solvent. Okay, so let's see here this one. Okay, just a minute. Okay, so now if I want to derive this one, mathematical expression for the vapor pressure of a solution. So what we have, the Raoult's law here, right? Pt is equal to P naught A XA plus P naught B XB. Okay, now what is this terms here? What is P naught A? P naught A is the pure pressure of A. Okay, XA is the mole fraction of A. Next, P naught B is the pure pressure of B. And XB is the mole fraction of B. Okay, so these are the four things we have. Now what is the condition here is, see, derive its mathematical expression of the vapor pressure of the solution. This is the vapor pressure of the solution, and just let me tell you that here A is a solvent, okay, and B is a solute. Right, now the question is saying of a non-volatile solute in a volatile solvent. So what that means, that A is volatile, okay, and B is non-volatile. Right, so now what I can do here, since B is non-volatile, that means P naught B will be 0. If B is non-volatile, means it will not evaporate, it will not create any pressure, so P naught B will be equal to 0. Right, this will be equal to 0. So if this is equal to 0, then what is the formula here? That is P naught A XA. Okay, so this is the formula that you need to derive here. Clear? And this is nothing but P, so I can write P total is equal to PA. Okay, so these are the two things that you need to derive. Next, draw a suitable level diagram to express the relationship for ideal solutions of A and B between vapor pressure and mole fraction. So this diagram we have, you have to draw on this x1 is equal to 1, x1 is equal to 0. So as the vapor pressure, as the mole fraction is decreasing, the vapor pressure will decrease, and for the x2, as the mole fraction is increasing, the vapor pressure will increase, and this line you have to draw, that is the total vapor pressure according to the Raoult's law. Next, match the following type of liquid-liquid solution with their characters. Okay, so this is a very different question. So in ideal solution, what happens? The ideal solution, you have P, the total pressure is equal to P naught A XA, delta H mix is equal to 0, and V mix is equal to 0. Right? So this one, then here this one, and this one. Now in non-ideal solution, what happens? Non-ideal solution with positive deviation, the total pressure is greater than the P naught A XA. it will have a positive delta H value and a positive V mix value. Now with a negative deviation, what happens? The pressure, the total pressure is less than P naught XA, and it has a negative delta H mix and negative delta V mix. Okay. Next, give the difference between ideal and non-ideal solution. So ideal obeys Raoult's law, does not obey Raoult's law. Delta H mix 0, V mix equal to not equal to 0. Here it is V mix is equal to 0, V mix not equal to 0. AB interactions are equal to AA, BB, and AB interactions are not equal to AA and BB interactions. Next, differentiate between the types of non-ideal solutions. You have positive and negative deviations. So positive deviation, here what happens is, in case of positive deviations, the AB interactions are weaker than AA and BB interactions, and here the AB interactions are stronger than AA BB interactions. Here P total is greater, here P total will be less. Delta H mix is greater than 0, delta H mix is less than 0. Okay, this one is not required. And here you can see the examples also. Okay, ethanol plus ethanol and acetone, and here a phenol and aniline. Next, differences between maximum and boiling azeotrope. So in maximum boiling azeotrope, where do we get that? We get that in case of negative deviation. They boil at a temperature higher than both of the solutions. Example is your nitric acid and water. And here we have shows positive deviation, and they boil at a temperature lower than the boiling point, and example will be ethanol and water. Okay. Next, show that the relative lowering of vapor pressure of the solution is equal to the mole fraction of the solute when solvent alone is volatile. Okay, so see here, we have calculated, so I'll show you, we have just calculated that P, the pressure when there is a non-volatile solute, the P total, okay, is equal to PA, right? Or this PA can be written as P naught A XA. Okay, or I can write this one as P naught A. Okay, just 1 minute, I'll write it from the starting. See, we get P total is equal to PA, right? We get in the, just now I have solved you, P total will be equal to PA. And what is PA equal to? P naught A XA, right? And how can I write this one? P naught A is equal to 1 minus XB. Okay, now if I just write down P naught A minus P naught A XB is equal to PA. Okay, then we have this one, P naught A XB is equal to P naught A minus PA. And if I have now XB is equal to P naught A minus PA by P naught A. And this is nothing but your relative lowering of vapor pressure. Okay, delta P by P naught is equal to XB, right? That is how we can calculate. So yes, I'll go to the next question. Yeah, so you can just see this in the book, and also I have derived it, so you can use that also. Okay, next is, question is, show graphically how the vapor pressure of a solvent and solution of a non-volatile solute changes with temperature. So you know that vapor pressure and temperature for the solution, as we have just discussed, relative lowering of vapor pressure. So solution vapor pressure will be less than that of the pure solvent. So now this is the vapor pressure of the pure solvent changing with temperature, and this is for the solution, right? And this is for the solution. Now after that, show on this graph the boiling point of the solvent and the solution. So if you see this one, where the vapor pressure reaches or meets the atmospheric pressure, that is the boiling point of the solvent, and this one where the vapor pressure of the solution meets the atmospheric pressure, that is the vapor pressure of the solution, right? Which is higher, and give reason for the answer. Which is higher here? Definitely you can see this T naught B. This is not like, this is the temperature here and this is the temperature here. So obviously this is the higher value, right? So what is the higher value? The vapor pressure. So I can write which is higher, boiling point of the solution is higher. Okay, now what is the reason for that? Now see, when you add a solute, the vapor pressure decreases. So now you have to add more heat to the solution to reach or to create that much vapor pressure to meet or to be equal to the atmospheric pressure. So that is why the boiling point increases. Now the boiling point of a solution increases when a non-volatile solute is added, because the solute lowers the vapor pressure. Boiling occurs when the vapor pressure of a liquid equals to the surrounding atmospheric pressure. pressure. Since the vapor pressure is lowered, a higher temperature is needed to reach the required pressure for boiling to begin. Okay, so that is how you have to explain this particular concept. Next, what is semi-permeable membrane, and give an example for each of them. So semi-permeable is a membrane which allows only, it is very important, only the solvent molecules to pass through it, but not the solute particles. Okay, it is commonly used to demonstrate osmosis. And natural semi-permeable, you have example cell membrane or animal bladder, and in synthetic membrane you have cellophane or parchment paper. Okay, next question. Let us see the next question. Next, see, match the following. Again, it is on the basis of your osmosis. So in isotonic solution, the concentration of NaCl is equal to 0.09% m by v. Okay, then what will happen? There will be no effect, no effect on neither enter nor leave the system. As a result, what will be the change in size? The size will be no change. Now hypertonic solution will have greater than 0.9%. okay, so that means what? Type, if it is hypertonic solution, the outer side solution is, now see, suppose you are talking about, there's a cell, okay, generally, and here we are mostly talking about blood cell. Okay, now inside the blood cell we have 0.9% NaCl. Now if in the outside, okay, if it is a hypertonic solution, the outside will have greater than 0.9 NaCl, greater than, that means what? This is more concentrated and this is diluted. Okay, in this case this is concentrated and this is diluted. So what will happen? The water will start flowing from this one. Okay, as a result of which the water will flow out of the cell, right? Water will flow out of the cell, okay, and it will shrink. Now if water will flow from here, it will start shrinking. Now in hypotonic solution, the outer cell will have less than, so water will flow into the cell, okay, and it will swell. Clear? Okay. Next, we have explained the desalination of water by reverse osmosis and name the semi-permeable membrane used in this. Now see, reverse osmosis is what? Osmosis is when you apply the correct amount of pressure to stop osmosis. But when you apply pressure greater than the osmotic pressure, the direction of osmosis is reversed, and that is called as reverse osmosis. And what is the membrane used here? Cellulose acetate. You can see the diagram also. Now see, initially what was the direction of osmosis? It was, osmosis was taking place in this direction. Okay, now when you applied exact pressure, you got pi. Now when you apply pressure more than the osmotic pressure, okay, here if you apply more pressure, what will happen? Water will be pushed out from this direction. The direction of osmosis is reversed from this semi-permeable membrane. Okay, now why do electrolytes show abnormal molecular masses? Name the factors responsible for abnormality. Okay, now see, electrolytes are those which can dissociate or associate in when you add them to the solutions, and as a result of which, see, electrolytes show abnormal molecular masses because they dissociate or associate in the solution, changing the number of particles and thus affecting the colligative properties. See, colligative properties, you know, it depends only and only on the number of particles, right? It doesn't depend on the nature of the particles. So when you have added the solution, when you have added the solute, after going to the solution, if it associates or dissociates, the number of particles changes, and as a result of which this one is affected. Next, factors responsible for dissociation. What are the factors responsible? The first factor is dissociation. Electrolytes like NaCl will dissociate, increasing the number of particles and lower observed molecular masses. Now see, so for example, I'll just take any one colligative property. Let us take delta Tb, okay, is equal to I into Kb into what is the given mass by molar mass into 1000 by mass of the solvent, Wb, Mb and Wa, right? Now what is the formula for molecular mass Mb? Okay, if I want to calculate molecular mass, it will become Kb into Wb into 1000 by Wa, right? Then we have, yes, one second, I have this one, then I have delta Tb value. Okay, now see, this is the formula. Now see, the colligative property depends on what? That depends on the number of particles produced. Now if the number of particles, if it has undergone dissociation, number of particles will be more. That means this colligative property which we have calculated will be more than the observed value. So when the colligative property, this particular value has increased, okay, because of the increase in the number of particles. If this one is increased, then what will happen? The molecular mass that you have, that you will actually calculate here, will be lesser than the original value. Okay, so electrolytes like NaCl dissociate into ions, increasing the particle number. So when they increase the particle number, the colligative property also increases, and then using this colligative property, when you calculate the molecular mass, that will decrease. And the opposite will happen in case of association. Now when the particles undergo association, number of particles will decrease, this value will decrease, and molar mass value will increase. So that is why we get abnormal molar mass. Next, based on the nature of their compounds, assume that the compound will undergo either 100% dissociation or 100% association. Compare the compounds with their Van 't Hoff factor. Okay, so you have to just match it. So see, K2SO4 will completely undergo dissociation, so you will get 2 plus 1 3. Okay, so this one is A, I'm writing here. Okay, next NaCl will also undergo dissociation, so this is B. Next FeCl3 or K3FeCl6. Okay, here also it will undergo dissociation. You will get 4 ions here, so that is your option. This is C. Then K4FeCN6, this also will undergo Al2SO4 whole 3. So 3 plus 2 5, 3 sulfate ion and 2 aluminium ion. You will get 5 ions. Similarly here 4 potassium ion and 1 whole, this complex will be 5 ion. So this one will be D. Okay, just see this one also I'll explain once again. You have 1 iron and 3 chlorine, so 4 particles, and you have 1 complex and 3 potassium, so you have here 4 particles, so that is why this is there. Now acetic acid in benzene, they actually undergo dimerization, so 2 particles will become 1 particle, so this is half. And urea or glucose are non-electrolytes, so they do not undergo any dissociation or association, so they have Van 't Hoff factor of 1. Okay, next you have to give reason questions. So from the last year in the midterm exams, in the model test papers, what factor or what different thing was observed is, see, where you will get this question, like this theoretical question. So let me just give a glance here. You have section C. Okay, in section C you will have first, I think 1 2, this is 4th question. Okay, you will have here inorganic 3 marker questions. Then in question number 5 you have physical questions. Okay, in that you will get 4 questions. Okay, 2 will be from electrochemistry, the 1 question will be from solution. But generally what I have found, this one 3 marker question is like this. You will have 3 bits and they will be asking you some reasoning questions here. Okay, that is what has been found in the trend. So I have brought you a set of 3 questions, 2 questions, like reasoning questions. You can think that it is something that you need to think from the concepts that you have learned, and these are not directly questions, these are all application based questions. Okay, so let us try them. Yeah, so first question, aquatic animals are more comfortable in cold water than in warm water. What can be the reason for here? Now see, the concept is from solubility of gases. If you remember, in the factors that affects the solubility of gases are more soluble. Gases are more soluble in cold water. So what will happen if the water is cold? There will be more oxygen present in that, right? So the aquatic animals will get more oxygen and they will be more comfortable. Okay, that is the first reason. Liquid ammonia bottle first cooled in the ice before opening it. Now see what happens here again. If suppose this is a bottle of liquid ammonia. Okay, now if you just open it, what will happen? The gas will evaporate. Okay, the gas will evaporate quickly. As a result of which what happens, that smell is so not toxic, but that is so suffocating and it can create problems. So that is why when we use this liquid ammonia bottle is first cooled. So when I have cooled the bottle to a very low temperature, the gases they have dissolved more. okay, like the dissolution of the gases has increased, more gases has dissolved, and now when you open they will release slowly and not in a very like fast way. Next, dissolution of some solid compounds is exothermic, while that of some others is endothermic. So, in some cases we need a temperature to dissolve a solid, so that is why it is endothermic. In some cases it releases heat, so that is why it is exothermic. Okay, so let's see now the answers here. How can you frame them? The first one, solubility of oxygen in water increases as the temperature decreases, and thus cold water contains more dissolved oxygen, which helps the aquatic animals to breathe easily. Second one, ammonia has a high vapor pressure at room temperature. Cooling reduces its vapor pressure, preventing the sudden escape of the gas and the loss of liquid ammonia when the bottle is opened. Next, the heat change during dissolution depends on the relative magnitude of lattice energy and hydration energy. So, if hydration energy is greater than lattice energy, then it will be exothermic. If hydration energy is less than lattice energy, then it is endothermic. Okay. Next, the vapor pressure of liquid is constant at a constant temperature. The vapor pressure of the solution of a non-volatile solute in a given solvent is less than that of the pure solvent. So, first of all, here what happens, the vapor pressure of a liquid is constant. So, if the temperature is constant, the water, there's a equilibrium process has been attained at a constant pressure, at a constant temperature. So, there is no more change in the number of particles or the number of molecules that is forming vapor, because at equilibrium, number of molecules forming vapor will be equal to the number of molecules condensing. And the second one, we all know, as I add more solute particles, they occupy the surface molecules, they allow less solvent particles to evaporate, making the vapor pressure lower, right? Now see, the vapor pressure of a liquid is constant at a constant temperature because at a fixed temperature an equilibrium is established between the liquid and its vapor pressure and its vapor. The rate of evaporation equals to the rate of the condensation, keeping the vapor pressure constant. Okay. Next, we have the vapor pressure of a solution of a non-volatile solute is less than that of the pure solvent because the solute particles occupy part of the surface, reducing the number of solvent particles that can escape into the vapor phase. This phenomenon is explained by Raoult's law. Okay. Next, an increase in the temperature observed on mixing the chloroform with acetone. So when you mix chloroform and acetone, okay, so there is a, how can I explain? See, an increase in temperature is observed on mixing chloroform and acetone. So when you have chloroform and acetone, it is a negative deviation. Okay, negative deviation, that means what? Interactions are stronger and there is release of energy. It is a delta H is also negative. There is release of energy, and this energy is used or is used in the raising of the temperature of that particular thing. Okay, so next, mixture of ethanol and acetone show positive deviation from Raoult's law. See, ethanol has strong hydrogen bonding, but when you add acetone to that, it disrupts the hydrogen bonding. So now the interaction between ethanol and acetone is very weak, so that is why it shows positive deviation. Pure ethyl alcohol cannot be obtained from rectified spirit even by fractional distillation. So that is because in rectified spirit this is an azeotrope. Okay, it is an azeotrope. Both the I can say both the liquid and vapor phase, both the components have the same boiling point, so you cannot separate them. Okay, so let's see the answers here. Yes, when chloroform is mixed with acetone, strong intermolecular hydrogen bonds are formed, releasing energy in the form of heat. Hence, there is an increase in temperature. Next, ethanol and acetone, when you mix, what happens? Shows positive deviation from the Raoult's law because the intermolecular forces between unlike molecules are weaker than those between the like molecules. So this increases the tendency of the molecules to be easily escape and increase the vapor pressure. Pure ethyl alcohol cannot be obtained from rectified spirit because this mixture forms an azeotrope. Okay, a constant boiling mixture that distills without any change in the composition. Clear? Yes. Next, oceans do not freeze. This is a very easy question. So in oceans there is a lot of salt that is added, not added by nature. There is so much salt present in the ocean water which has decreased the freezing point to such a low extent that oceans do not freeze easily. Water stops boiling when sugar is added. So when you add sugar, what will happen? the boiling point will rise, right? Suppose now the temperature was 100 degrees Celsius and the water was boiling. You added some sugar to that. So now the boiling point will become, the boiling point of water will become 102, for example. But water is still at 100 degrees Celsius, right? So that is why it will not boil. It will take some time till the boiling point now reaches till 100, till the temperature of water reaches till 102 degree. Again it will start boiling, but at that particular time it will stop. Next, the freezing point of a solvent is lowered on dissolving a non-volatile solute in it. So we know that freezing point, how do we explain freezing point? See, if I have a graph like this, okay, you have, this is suppose pure solvent and this is solution, okay, and you have, this is another, okay. See, this is what, this is pure solvent vapor pressure and this is liquid vapor pressure, okay. Pure solvent this is liquid vapor pressure and this is solid vapor pressure. Now when this this is of the solvent, okay. Now when you have a solution, okay, now when we have a solution, what happens? When this solution touches this one, that is vapor pressure, solid vapor pressure, at that point freezing will take place, okay, when this one has to touch here. So you can see this is the initial freezing point and now the freezing point has decreased. So why the freezing point decreases? Because when we add a solute, the vapor pressure decreases, right? So yes, let's see this one. So oceans do not freeze because they contain a large amount of dissolved salts, which lowers the freezing point of water. Next, water stops boiling when sugar is added because it increases the boiling point. You can read the answer. The freezing point of a solvent is lowered when a non-volatile solute is dissolved in it because its vapor pressure of the solution has decreased, and now you need to go to more lower temperature to meet the vapor pressure of the solvent, okay. Next, while making ice creams in a metal or plastic cones, the ice cream seller puts a mixture of ice and the common salt around the cones and not ice alone. So this is very simple. When you add a mixture of salt, again the vapor pressure decreases and the freezing point decreases. So now the freezing means it will become more cold and ice cream can stay in the colder state for a longer period of time. Next is when fruits and vegetables have dried are placed in water, they slowly swell and return to the original form. So this is because of endosmosis. When you keep the fruits and vegetables in a diluted solution, water starts flowing into it due to osmosis, and that is why the shape regains. Cutting onions taken from the fridge is more comfortable than cutting onions lying at the room temperature. I would rather do that. So what happens here is when you have when you have onions, they create a certain type of vapor, okay, which is so irritating for the eyes and we get tears. But when the fridge, when you keep the onions in the fridge, okay, so this vapor pressure release is very slow, and when you bring it out, due to the low temperature, the vapor pressure, the vapors are not formed by the onions, and that is why we get we do not get these vapors and there's no irritation, as a result of which we can also cut without getting any hurt in the eyes. So here you can see the first one I have already explained. This is also explained. Cutting onions from the fridge is more comfortable because low temperature reduces the volatility of the chemicals, okay, that cause the eye irritation, hence fewer vapors are released and eyes don't water much. Okay, next we have some diagram based questions. So for this graph, answer the following questions. What type of non-ideal solution is this one? So you can see the deviation is towards the positive side, so this is a positive deviation. Okay, let me write down here, it is a positive deviation. Next, what is there? Give example of such type of non-ideal solutions. So examples we have just discussed, we have ethanol and CS2. Okay, this is a positive deviation. What type of azeotrope will the mixture A and B form? So when you have a positive deviation, that means the interactions are weak, so they form minimum boiling azeotrope. Okay, minimum boiling azeotrope is formed. Next question, analyze the given graph and again you have to answer. Write the expression for the calculation of vapor pressure of liquid A in the solution at any concentration. Okay, so write the expression for the calculation of vapor pressure of liquid A in the solution at any concentration. Okay, so to calculate only the vapor pressure of A, you need the formula P naught A into XA. Okay, at any point, for example at this point, you can just calculate. Okay, so what is the pressure at this one? That will give you this one. So P naught A into XA. Next we have give example for solutions that show this type of plot. So this is an ideal solution. So for ideal solution you have examples, right? N-hexane and N-heptane. So now see, they are not directly asking you the question. They have tricked the question in the form of graph and then they are asking you the examples. Next, whether the formation of solution is exothermic or endothermic formation of solution. So in this case, in the case of ideal solution, the delta H mix is 0. That means it is neither endothermic nor exothermic. What is the value of delta H mixing and delta V mixing for this solution? Yes, delta H mix is also 0 as we have just discussed, and delta V mix is also 0. Okay, clear? Next, we'll do some numerical based questions. So, okay, calculate the mole fraction of benzene and carbon tetrachloride in a solution made by dissolving 20 gram of benzene and 80 gram of carbon tetrachloride. This is very simple question. You have to calculate the mole fraction of benzene. So, first let us write down all the given values. So, what is the mass of benzene? 20 gram of benzene, right? So, here I have 20 gram of benzene, and what is the molar mass of benzene here? You have 78 gram of benzene. Okay, now what is the number of moles of benzene then? That is equal to 20 by 78. Now here we have what is W of CCl4 carbon tetrachloride, that is 80 gram, and the molar mass of carbon tetrachloride, okay, and that is equal to how much? 154 gram per mole. Now what is the number of moles of CCl4, which is equal to 80 by 154. Okay, now let's calculate the mole fraction of benzene. So mole fraction of benzene will be, see, if I want to calculate mole fraction of benzene, it is number of moles of benzene divided by number of moles of benzene plus number of moles of carbon tetrachloride, which is equal to, you have 20 by 78 divided by 20 by 78 plus, here you have 80 by 154. Okay, now if I solve this, you will get mole fraction of benzene, which is 0.33. Now if I want to calculate the mole fraction of carbon tetrachloride, it will be 1 minus 0.33, which is equal to 0.67. Clear? Next, the mole fraction of helium in a saturated solution is given. Find the pressure of helium above the solution given Henry's constant is this one. This is very simple question. We have this formula, P is equal to KH into mole fraction, right? So the question is asked to find the mole fraction of helium, right? So mole fraction of helium will be pressure of helium by KH value, right? What is the value for pressure of helium? That is, we have to find the pressure. Okay, sorry, this is not required then. So I can directly now substitute. So what is the value of KH? KH value is 144,970 into 1.2 into 10 to the power of minus 6, and that will give me how much? Yeah, and that will give me 0.174 bar. Okay, 0.174 bar. Don't forget to write the units here. Okay. Next, the vapor pressure of pure liquid A is 40 mm of Sg, and the vapor pressure of this liquid in solution with liquid B is dash mm of Sg. Okay, this I think some value is missing. Let me just correct it. Okay, calculate the mole fraction of A in the solution if mixture obeys the Raoult's law. Okay, I checked the question. Here it is actually 32. Okay, 32 mm of Sg. Let us see the next question here. The vapor pressure of liquid A is 40 mm of Sg at 310 Kelvin, and the vapor pressure of liquid in the solution with liquid B is actually 32. Okay, this is missing. So calculate the mole fraction of A in the solution if mixture obeys Raoult's law. Okay, so we have this formula, P total is equal to P naught A XA plus P naught B XB. right? Now if I just want to know about the mole fraction of A, then I can just write down this also in the form of, see, P naught A XA plus P naught B 1 minus XA, right? The vapor pressure of pure liquid A is 40. So what is P naught A? That is 40, okay? And the vapor pressure of this liquid in solution with liquid B is 32. Let us see the next question. The vapor pressure of pure liquid A is 40 mm of Sg. The vapor pressure of this liquid, means it is the vapor pressure of A only. Liquid A in the solution with liquid B is 32. Okay, here there is a missing 32 mm of Sg. Calculate the mole fraction of A. Now see, suppose the question is saying that you have a mixture A and B. Okay, so here PA, when it is with B, the pressure is 32, and when you have only A, okay, and at that time the pressure P naught A is equal to 40, right? So what is the formula here? PA is equal to P naught A XA. Okay, PA is 32 and P naught A is 40 into XA. Okay, so 32 by 40 is equal to XA. So 4 8s are 4 10s are, and XA is equal to 0.8. Okay, clear? Next we have the boiling point of benzene is 353.23 Kelvin when 1.8 gram of a non-volatile non-ionizable solute was dissolved in 90 gram of benzene. The boiling point raised to this much. Calculate the molar mass of the solute. Kb for benzene is given. So this is direct question from this formula, that is delta Tb is equal to Kb into m. Now here if I just want to expand this one, so I will have Tb minus T naught B is equal to Kb into given mass of the solute by molar mass of the solute into 1000 by mass of the solvent. Okay, so now what is Tb here? 354.11. okay, minus what is Tb here? 353.23. okay, Kb value is 2.53. okay, Wb value is how much? Given mass is 90 grams, no sorry, 1.8 gram, just a minute, eraser, this is 1.8 gram. okay, the molar mass is, the boiling point of benzene is, so molar mass I have to calculate, right, into 1000, right, by mass of the solvent is 90. Now you have calculator in the exam, you don't have to worry, just you need to calculate this MB value, and once you calculate you will get 57.27 gram per mole. Okay, next question, 1 gram of a non-electrolyte solute is dissolved in 50 gram of benzene. Lowered the freezing point of benzene by 0.4 Kelvin, find the molar mass of the solute. Even here the question Kf value is also given. Again very similar question, we have delta Tf is equal to Kf into molality, where I have Wb by MB into 1000 by WA, right? So what is Kf? Tf value is 0.4. What is Kf value? That is 5.12. okay, Wb is 1 gram, molar mass I have to calculate into 1000 by mass of the solvent is 50. okay, so now if I solve this, and I'll get MB value equal to 256 gram per mole. Now let's see, yeah, so these were the most important questions. Now let's see the most important topics from this chapter. The first topic is definitely you need to know Henry's law, applications of Henry's law and everything. You need to know Raoult's law, its formula, numericals, colligative properties, super important. All the numericals will be asked from this one maximum, so please try to solve these questions. And yes, Van 't Hoff factor is also there. Okay, so students, that's all in this video, and I hope this video was helpful. And do not forget to subscribe the channel, because we are coming up with many such important chapters, and these all questions were from your new question bank that has been released by the government. So yes, definitely you will be able to practice more questions. So do subscribe the channel, and all the best for your exam. Thank you so much.